Welcome. This is a design video for ECE 4960 Senior Design. The project we were assigned was the balancing robot. Project members include Kyle Campbell, Jackson Kramer, Patrick Freeman, Ethan Lupnick, and Rand Maubrey.
Hey, where you going, little buddy?
The assigned project was building a two-wheeled robot autonomously capable of staying upright. The robot was also required to move forwards and backwards in turn given directions from an external controller. A TiVo microcontroller was required as the primary controller, and all the power for the system was required to be self-contained from an onboard battery. A robot shown here was made to balance and move using programming from MATLAB and Simulink. The basis of the programming is to use two feedback loops. Constantly taking the angular velocity of the robot, the microcontroller is programmed to compute the required information to send to the motors to keep the robot balancing. To better explain how this works, it would make more sense to start with how the motor tracking works. To start with wheel tracking, encoders were attached to our wheel motors. These encoders send signals to our LS7366R counter chips, which keep track of the movement. A display is set up here to show how the movement of the wheels affect the count. For each rotation, there are 1200 counts. Rotating one way counts up, while rotating the other direction counts down. Knowing this count allows us to keep both wheels at the same position. This is done by making one wheel the master and the other the slave. The slave wheel simply tracks the count of the master and attempts to mimic its count. With this motor tracking, there will be no difference in how the two motors move. Without this wheel tracking, sending the same signal to each motor could result in slight differences due to different motor characteristics. Now that the wheel tracking has been explained, we can move on to how the input to the motors is found. Our IMU, or inertial measurement unit, was placed center height on the robot to read its angular position. This constant reading is sent to our TiVo microcontroller. After calculating the physical characteristics of the robot, we were able to create a PD controller that could be used to balance the robot. Taking in the current angle position and comparing it to the desired angle of 90 degrees, or upright, the PD controller is able to determine the required output. This is converted to voltage and then to required duty cycle of the PWM signal, which is to be sent to the motors. This is one of the two feedback loops that are required. The other is monitoring the speed of the wheels. Using only a derivative controller for this system, the speed is input from the counters and is compensated by the system to obtain a desired speed. This desired speed is what can be changed to allow the user to tell the robot to move. This project was very interesting and fun to do. Although quite challenging at times, it was rewarding to get results. Thank you for watching.